You're staring at your screen when the alert comes through. March 11th, 2025, 3:47 AM UTC. An interstellar visitor. Something that has crossed the void between stars for millions of years. Just exploded near the sun. You pull up the data. The brightness curve spikes violently, magnitude 18 to magnitude 8 in hours. Your hands freeze over the keyboard. This shouldn't be possible. The timing is too precise. The energy signature is all wrong. The fragments are moving in directions that violate every comet model you know. 3I/Atlas. Our third confirmed visitor from another star system. Just died in a way that makes no scientific sense. And sitting here, watching the numbers scroll across your screen, you realise something chilling. We might be watching something that was never a comet at all. If mysteries like this are why you're here, stick with me through this investigation, and when something grabs you, hit like and subscribe so we can chase these answers together. Drop a comment with your theory, natural breakup, or something else. Now, let's go dark, turn down the lights, and examine what really happened out there. You're still staring at that data. The numbers don't lie, but they're telling you a story that shouldn't exist. Your coffee's gone cold 3 hours ago, but you haven't moved, because right now, in this moment, you're holding evidence of something that's rewriting the textbook on interstellar objects. And the strangest part, nobody saw it coming. Let me take you back to where this all started, not to March 11th when everything exploded, but to January 14th, 2024, a Tuesday. Nothing special about it, really. The Atlas Survey telescope in Hawaii was doing what it does every clear night, scanning the sky. Cataloguing asteroids, tracking near-Earth objects, automated, routine. The kind of work that's supposed to be boring. And then, at 4:23 AM local time, the detection algorithm flagged something unusual. Object designation C2024A1. Just another comet candidate. Right. That's what the first astronomer who reviewed it thought. You pull up the preliminary images, a faint smudge. Magnitude 19, barely visible. Nothing dramatic. But here's where your training kicks in. You run the orbital calculation, plugging in the position data, the velocity vectors, the trajectory arc, and then you see it. The eccentricity value 1.043. If you're not an astronomer, that number might not mean much to you. Let me put it this way, any orbit with an eccentricity above 1.0 is hyperbolic. It's not bound to the sun, it's not coming back. This object is just passing through, like a stranger walking through your town on their way to somewhere else. Except this stranger didn't come from the next town over. They came from another solar system entirely. You feel that little rush, don't you? That moment when you realise you're looking at something from out there? The third confirmed interstellar object in human history. The first was Oumuamua in 2017, that cigar-shaped mystery that caused all the debates about solar sails and alien probes. The second was 2I/Borisov in 2019, a more well-behaved comet that at least looked like something we understood. And now, 3I/Atlas. Your discovery. Well, Atlas's discovery, but you're the one analysing it now. The confirmation process moves fast. Within 48 hours, observatories worldwide are tracking it. The Minor Planet Center officially designates it as an interstellar object on January 17th. The press releases go out. Third interstellar visitor discovered. Social media lights up with speculation. Is this one going to be weird like Oumuamua? Is it going to accelerate mysteriously? Will it look artificial? But here's what makes you uneasy, even back then. You run the trajectory backwards, tracing where this thing came from. The calculations show it entered our solar system from the direction of the constellation Lyra, travelling at 28 kilometers per second relative to the Sun. That's 62,600 miles per hour fast. but not unusual for interstellar speeds. You can trace its path back millions of years, watching it drift through the galaxy, a frozen relic from some ancient star system we'll probably never identify. What bothers you is how clean that trajectory is. When objects travel through space for millions of years, they get nudged, gravitational interactions with passing stars, collisions with interstellar dust, radiation pressure, there should be perturbations, wobbles in the path. But 3I/Atlas's trajectory is almost pristine, like someone drew a straight line with a ruler across the galaxy. Probably just lucky, your colleague says when you mention it. Sometimes things just travel through empty space. Maybe, but you make a note of it anyway. By February, the observations are piling up. You're tracking 3I/Atlas as it falls inward toward the Sun. The orbital mechanics tell you it'll reach Perihelion, its closest approach to the Sun, on March 12th, 2025. At that point, it'll be about 0.65 AU from the Sun, roughly 60 million miles, inside the orbit of Venus. For an interstellar comet coming from the frozen depths of space, that's going to be intense. The Sun's heat will hit it hard. You expect it to brighten as ice sublimates, maybe develop a spectacular tail. Standard comet behaviour, but then the anomalies start. Late February 3I/Atlas brightens suddenly, jumping half a magnitude in a single night. No gradual increase, just a spike. Outburst. The reports call it. Comets do this sometimes when a pocket of volatile material vents suddenly. You've seen it before. Nothing to worry about, except 3 days later, it happens again, and then again, a week after that. Each outburst seemingly random, no pattern you can predict. Dr. Michelle Bannister at the University of Canterbury publishes an observation note that catches your attention. The outburst timing and magnitude do not correlate with solar distance as expected for thermal-driven activity. She's being diplomatic. What she means is this doesn't make physical sense. When comets warm up, they brighten gradually as they approach the Sun. They don't flicker on and off like a broken light bulb. You're not the only one noticing. By early March, there's a dedicated observing campaign. The Hubble Space Telescope allocates time. JWST turns its infrared eye toward it. Ground-based observatories from Chile to Arizona are tracking it every clear night. The data streams in spectroscopy, photometry, polarimetry. You're building a profile of this object, trying to understand what it's made of, how it's behaving. The spectroscopic data is weird. Normal comets show strong emission lines from water ice, carbon dioxide, methane, the usual suspects. 3I/Atlas shows those, but the ratios are off. There's too much of something you can't quite identify. A spectral feature that doesn't match any known comet composition. Probably just unusual chemistry from wherever it formed. The team lead says during a video conference, different star system, different composition. Sure. But you're starting to get a feeling. That itch at the back of your mind when the data's trying to tell you something but you can't quite hear it yet. March 10th, 2 days before Perihelion, you're monitoring the brightness curve in real time now, along with dozens of other astronomers worldwide. There's a Discord channel that's been set up specifically for 3I/Atlas observations, people sharing images, posting measurements, debate and interpretations at all hours. Someone posts a light curve showing another outburst, then another. The object is becoming unstable. Probably just pre-perihelion heating, someone types. It's getting close to the Sun. This is normal. Except your gut is telling you it's not. March 11th, 3:47 AM. You're in that moment again. The alert. The spike. And suddenly, normal is the last word that applies to anything about 3I/Atlas. Because what happens next doesn't just break the pattern, it shatters every assumption we had about what interstellar visitors are supposed to do when they visit our Sun. But before we get to that explosion, We need to understand what makes 3I/Atlas so fundamentally different from anything else that's ever visited our neighbourhood. Because the moment you confirmed that hyperbolic orbit back in January 2024, you weren't just looking at another comet. You were looking at a time capsule from a place we've never been. Think about this for a second. Every comet you've ever heard of, Halley's Comet, Hale-Bopp, Neowise, they're all locals. They were born here, in our solar system, probably in a region beyond Neptune called the Kuiper Belt, or even further out in the Oort cloud. They've been orbiting our sun for billions of years, occasionally getting kicked inward to put on a show for us. They're family. 3I/Atlas is not family. It's a stranger who wandered in from the cosmic highway. When you trace its origin back, really back, the numbers start to blow your mind. That 28 kilometers per second velocity, that's its speed relative to the local standard of rest. The average motion of stars in our region of the galaxy. It means 3I/Atlas has been travelling through the Milky Way for an incomprehensibly long time. Your simulation models suggest it could have been wandering for anywhere between 5 million to 50 million years. Imagine that. Humans didn't even exist when this thing started its journey. Dinosaurs might still have been walking around Earth when 3I/Atlas got ejected from whatever star system created it. And here's where it gets personal for you as an astronomer. You'll never know where it came from. Not precisely. You can trace the trajectory back and say, it came from the general direction of Lyra, but that's pointing at a region of sky containing thousands of stars. Was it born around a sun-like star, a red dwarf, a binary system? Did it form in the outer reaches of a planetary system and get gravitationally ejected during some ancient planetary migration event? Or was it created in the debris disk of a young star and just drifted away? The not knowing drives you a little crazy. Doesn't it? Let me give you some context for how rare this is. Our galaxy contains somewhere between 200 to 400 billion stars. Each of those stars probably has planets. Many of those planetary systems probably created comets and asteroids during their formation. Some of these objects got kicked out into interstellar space. Statistically, there should be trillions upon trillions of rogue comets and asteroids drifting through the galaxy right now. A 2018 study by researchers at Harvard estimated that there could be as many as 10 circumflex 15 interstellar objects per cubic parsec in the Milky Way. That's a lot of cosmic debris. But here's the problem. Space is really, really empty. The chances of one of those objects randomly passing through a tiny little solar system, astronomical. Literally. We're talking cosmic lottery odds. Yet in just 8 years from Oumuamua in 2017 to now, we've detected 3 of them. 3. Does that seem weird to you? Because it seemed weird to a lot of astronomers. After Oumuamua, scientists did the math. Doctor. Greg Laughlin from Yale calculated that we should expect an interstellar visitor to pass through the inner solar system only once every few decades at most. Some estimates were even more conservative, once per century. So why 3 and 8 years? 2 possibilities. Either we got extraordinarily lucky and we're living through a statistical fluke, or there are way more interstellar objects passing through than we thought. The optimistic take is that our detection capabilities have just gotten that good. Atlas, Pan-STARRS, the Catalina Sky Survey, these automated systems scan huge swaths of sky every night. We're finally seeing what's been there all along. But you, sitting there analysing 3I/Atlas, you can't shake a third possibility. What if some of these visitors aren't just random debris? What if some of them are intentional? Okay, I know what you're thinking. Here we go with the alien stuff. And look, I get it. Scientists have to be careful about speculation, but stay with me here, because this is where 3I/Atlas starts to look genuinely strange in ways that Oumuamua and Borisov didn't. Oumuamua was weird, no question. That tumbling, elongated shape. The non-gravitational acceleration that suggested something was pushing it either outgassing we couldn't detect, or, as Harvard astronomer Avi Loeb controversially suggested, a light sail. But Oumuamua also moved really fast through the inner solar system. We detected it on October 19th, 2017, and by January 2018 it was already too far away and too faint to observe. Blink and you miss it. We got tantalizing hints of weirdness, but not enough data to really understand it. Borisov, discovered in August 2019, was almost disappointing by comparison. It looked like a normal comet. It had a proper coma, a tail. It outgassed predictably. Spectroscopy showed it contained water ice and cyanide compounds, just like our local comets. It was interstellar. Sure, but it was boring, comforting, even. Astronomers could say, most interstellar objects are probably just normal. But 3I/Atlas, it's threading a needle between those two extremes, and that's what makes it so unsettling. It's active like Borisov, showing outgassing, brightening, comet-like behaviour, but the details are wrong in subtle, persistent ways that keep adding up. Those random outbursts, that pristine trajectory, that weird spectroscopy, and you haven't even gotten to the explosion yet. There's something else about the trajectory that bothers you. Something you haven't told many people because it sounds too conspiratorial. When you calculate 3I/Atlas's path through the solar system, it doesn't just pass through randomly, its perihelion point. That closest approach to the Sun puts it in a position where it's highly visible from Earth for weeks leading up to the event. If you were designing a flyby to be observed by a civilization on the third planet, you'd pick a trajectory almost exactly like this one. Coincidence? Probably. Space doesn't care about our viewing angles. But the thought nags at you during these late-night observation sessions. What if someone wanted us to see this? You run the numbers again, double-checking. The orbital inclination 94.8 degrees. That's almost perpendicular to the plane of the solar system, which is unusual but not impossible. The velocity at infinity 12.7 kilometers per second. Again, within the expected range for interstellar objects. Everything checks out. Everything is technically normal. But normal doesn't usually give you goosebumps. By March 10th, you got a comprehensive dataset on 3I/Atlas. You know its rotation period approximately 8.3 hours, though that measurement's been getting harder to pin down as the outbursts increase. You know its approximate size somewhere between 500 to 800 meters in diameter, making it larger than Oumuamua, but smaller than a typical short-period comet. You know its albedo is low, around 0.04, meaning it reflects only 4% of the light that hits it. Dark, ancient, scarred by millions of years of cosmic radiation. You think you understand this object. You've categorized it, measured it, fit it into your models. It's weird. Sure, but you've got a handle on it. You know what to expect when it reaches perihelion. You don't know anything at all. Because in about 37 hours, 3I/Atlas is going to teach you that sometimes the universe has no interest in meeting your expectations. March 11th, 2025. Perihelion minus 20 hours. You haven't slept. Not really. Maybe you dozed off in your chair around midnight for 45 minutes. But that hardly counts. Your observation window at the telescope opens in 3 hours. And right now, you're watching the pre-dawn data roll in from observatories on the other side of the planet. Australia, Chile, South Africa. Everyone's locked onto 3I/Atlas now. This is the vigil, the countdown. Have you ever waited for something you knew was going to be significant but had no idea how? That's where you are. It's like standing on a beach watching a tsunami approach, except you don't know if it's going to be 3 feet tall or 30. The anticipation is almost physical. The Discord channel has 247 people online at 4 a.m. on a Wednesday. That tells you everything about how the astronomical community is treating this event. Messages scroll past brightness measurements, spectral observations, someone sharing a time-lapse animation of 3 ice/atlases approach, Doctor. Alan Fitzsimmons from Queen's University Belfast posts outburst activity increasing in frequency. 7 distinct events in the past 72 hours. Magnitude fluctuations becoming more pronounced. You pull up your own observation log. He's right. The outbursts that used to happen every few days are now happening every few hours. It's like watching someone's heartbeat accelerate before a sprint. The object is responding to the sun's heat, but not in any smooth, predictable way. Each spike in brightness is sharp, sudden, then fades back to baseline. On and off, on and off. Someone in the Discord asked the question everyone's thinking, is it going to survive Perihelion? Good question. Let me tell you about comets that didn't make it. December 2013 comet Ison, hyped as the comet of the century, approached the Sun with a perihelion distance of just 0.0124 AU, about 1.2 million miles. That's close. Really close. You watched that one too, along with millions of people worldwide who'd been promised a spectacular show. Ison came around the Sun, brightened dramatically as predicted, and then nothing. It disintegrated, torn apart by tidal forces and thermal stress. The disappointment was crushing. No great comet, just a debris field. July 1994, comet Shoemaker Levy 9 didn't even make it to the Sun. Jupiter's gravity ripped it into at least 21 pieces, which then slammed into the planet one after another in the most spectacular cosmic collision humans have ever witnessed. The impact scars were visible for months. Each fragment hit Jupiter with the energy of millions of nuclear bombs. Comets are fragile. That's the lesson. They're not solid rocks. They're dirty snowballs. As astronomer Fred Whipple described them back in 1950, loose aggregations of ice, dust, and rock held together by weak gravity and frozen volatiles. When you heat them up or stress them gravitationally, they fall apart. It's not a question of if, it's a question of when. So the real question isn't, will 3 ice/atlas survive? The real question is, should it survive at 0? 65 AU is going to be hit with solar radiation intensity about 2.4 times what Earth receives, for an object that's spent millions of years at temperatures barely above absolute 0. That's a shock. The surface temperature is going to spike to something like 400 Kelvin, about 260 degrees Fahrenheit. Any water ice near the surface will sublimate violently. Carbon monoxide, carbon dioxide, methane, all the volatile ices will boil off simultaneously. The object should brighten. It should develop a spectacular coma and tail as material streams away. It should look like a comet doing comet things. And then, if it's weak or already fractured from those strange outbursts, it should break apart gently, probably. A fragmentation event spread over hours or days as thermal stress cracks propagate through the nucleus. That's the script. That's what you're expecting. Textbook comet behaviour at Perihelion. You have no idea that the script is about to be shredded. March 11th, 11:00 AM your local time. Perihelion -9 hours. You're at the telescope now, running final checks on the instrumentation. The weather is perfect clear skies, low humidity, minimal atmospheric turbulence. It's like the universe is giving you front row seats. You've configured the CCD camera for rapid photometry, taking images every 30 seconds. High temporal resolution. You don't want to miss anything. Your colleague, Dr. Sarah Chen, is at the spectrograph station. I'm getting really weird emission lines, she says, not looking up from her screen. The CN bands are stronger than they should be, and there's this feature at 388 nanometers that I can't identify. Organic compounds, you suggest? Maybe. Or something we haven't seen before? She sounds excited. This is why people become astronomers, not to catalogue the expected, but to glimpse the unknown. The hours crawl by. You're monitoring 3i/Atlas continuously now, watching as it creeps toward that mathematical point of closest approach. The object is at magnitude 10.3 visible in amateur telescopes if you know where to look. Brightness steady for the moment. No outbursts in the past 4 hours, which is actually unusual given the recent pattern. It's like the calm before no. Don't think that. Don't jinx it. Perihelion minus 3 hours. You step outside for a moment just to clear your head. The sun is setting, painting the sky in oranges and purples. Somewhere up there, invisible in the daylight, 3i/Atlas is making its closest approach to our star. In 3 hours, it'll pass that exact point and begin its outward journey, accelerating back toward interstellar space, never to return. This is your only chance, humanity's only chance. Whatever happens in the next few hours is all we're ever going to see of this visitor. You think about all the people watching. Not just professional astronomers, there are probably thousands of amateur astronomers setting up telescopes in their backyards right now. From California to Maine, waiting for darkness. There are live streams being prepared. Social media posts counting down. For the general public, this is entertainment, a celestial show. But for you, it's something else. It's a conversation with the cosmos, a chance to ask, what are you? Where did you come from? What can you teach us? You head back inside. Perihelion minus 90 minutes. The data feed from the Australian observatories shows 3i/Atlas, brightening slightly magnitude 9.8 now, normal, expected. As it gets closer to the sun, more material sublimates, basic physics. You're watching the light curve on your monitor, that rising line tracking the increase in brightness. Smooth, gradual, perihelion minus 45 minutes, magnitude 9.3. Perihelion minus 20 minutes, magnitude 8.9. Sarah looks over at you. Right on track. Looks like it's going to be a clean perihelion passage. Maybe, you say, but that uneasy feeling hasn't left. You've learned to trust your instincts over the years, even when the data seems fine. Perihelion minus 5 minutes. You hold your breath without meaning to. This is it. The moment of closest approach. If 3i/Atlas is going to break apart from tidal stress, it'll happen right about perihelion. March 12th, 2025, 0017 UTC, magnitude 8.7, holding steady. 1 minute past perihelion, still steady. 2 minutes past. 3, Sarah exhales. Looks like it's holding together. Tough little thing, isn't it? You nod, starting to relax. Maybe this will just be a successful perihelion passage. Maybe 3i/Atlas will give us good data as it heads back out, and we'll write papers about its unusual composition and those strange outbursts. And in a few years, it'll be magnitude 8.1. You blink. That's wrong. It shouldn't brighten that much that fast. You check the photometry settings. Everything's correct. This is real. Magnitude 7.4. Sarah. I see it. Her voice has changed. Sharp, alert. Magnitude 6.8. The light curve on your screen isn't gradually rising anymore. It's spiking. Vertical, like someone just flipped a switch. Magnitude 6.1. This isn't outgassing. This isn't normal. This is... And that's when 3i/Atlas doesn't just break apart. It doesn't gently fragment like Ison did, slowly crumbling into pieces over hours. No, it explodes with the kind of violence that makes you instinctively lean back from your monitor, even though you're watching something happening 60 million miles away. The numbers are screaming at you now. Magnitude 5.2, then 4.8. The light curve isn't just spiking, it's going nearly vertical on your screen. In the span of 8 minutes, 3i/Atlas has brightened by more than 4 magnitudes. That's a 16-fold increase in brightness. You're watching energy pour out of this object at a rate that shouldn't be possible for a comet. Get the spectrograph on it. Now, you shout to Sarah. Your hands are already moving, Nicole, reconfiguring the imaging sequence, shortening the exposure times, because the object is getting so bright it's going to saturate your detector if you're not careful. This is the kind of problem you never thought you'd have with something that was magnitude 19 just 14 months ago. Sarah's fingers fly across her keyboard. Spectrograph is tracking. Oh my god, look at these emission lines. You don't look, can't look. You're focused on the photometry, on capturing every second of this event because you know that what you're witnessing right now is going to be in textbooks someday. Or it's going to rewrite the textbooks entirely. Magnitude 4.1. You can see it with the naked eye now if you know exactly where to look. A star that wasn't there before, glowing in the pre-dawn sky. The Discord channel has exploded. Messages pouring in from observatories worldwide. Everyone's seeing this. The Australians caught the initial brightening. Hawaii just got darkness and their telescopes are slewing to the target. Someone from the Canary Islands is posting real-time images showing a rapidly expanding debris cloud. The professional astronomy community is watching history unfold in real time. And nobody is staying calm about it. Dr. Matthew Knight from the Naval Research Laboratory posts. This is not typical cometary fragmentation. Energy release is orders of magnitude higher than thermal stress models predict. You want to reply, want to join the discussion, but you can't take your eyes off your own data. Because now you're seeing structure. The brightness isn't uniform, it's pulsing. 3 distinct peaks, each separated by about 11 minutes. The first wave peaked at magnitude 3.9, then it faded back to 5.2, then another surge to 4.3, then another fade to 5.8, and now a third surge building magnitude 3.2. What natural process produces 3 separate energy pulses with that kind of timing? You're running through the physics in your head. Could it be 3 separate fragments, each undergoing catastrophic disruption at slightly different times possible? If the original nucleus had fractured into pieces during those earlier outbursts, and each piece had a slightly different composition or structural integrity, they might fail sequentially as they round the sun. But 11-minute intervals, that's too regular, too precise. Natural processes aren't that punctual. The third pulse peaks at magnitude 2.8, bright enough to see easily with the naked eye now, like a moderately bright star, and then begins to fade. Your heart is pounding. You're recording everything, every frame, every data point. Your observation logs are going to be crucial for understanding this event. By 0045 UTC, just 28 minutes after Perihelion 3 I/Atlas has faded back to magnitude 7.1, still much brighter than it was before the explosion, but the dramatic light show is over, or at least this phase of it is. You finally allow yourself to look at Sarah's screen. The spectroscopic data is bizarre. During those brightness pulses, the emission lines went crazy intense spikes of sodium, potassium, calcium, materials you'd expect to see if you were vaporizing rock, not just sublimating ice. The temperatures required to produce those emission spectra are in excess of 2000 Kelvin. That's not comet warming up in sunlight temperatures. That something is catastrophically fragmenting and releasing kinetic energy temperatures. Did we just watch it blow itself apart? Sarah asked quietly. Yes, you say. But the question is how, and why at that exact moment? Let me give you some context for what you're feeling right now, because I want you to understand just how unprecedented this is. Comets break apart near the sun all the time. Well, not all the time, but it's a known phenomenon. We've documented dozens of cases, but they almost never do it like this. Take comet linear C1999S4, which fragmented in July 2000. You studied this one during your graduate work. Linear broke into multiple pieces over the course of several days as it approached perihelion. The breakup was gradual. First the nucleus started shedding fragments. Then those fragments drifted apart, each developing its own tiny coma. The brightness increased. Sure, but spread over days, not minutes. It was like watching a sandcastle slowly dissolve in the tide. Not like watching it get hit by a wave runner. Or Comet 73P/Schwassmann-Wachmann 3, which disintegrated spectacularly in 2006. That one broke into at least 68 separate fragments that astronomers actually named Component B, Component C, all the way through the alphabet and beyond. But again, this happened over weeks. The comet had been showing signs of instability since 1995. The final fragmentation was dramatic but not sudden. Nature gave us warnings, time to prepare, time to understand. 3i/Atlas gave you 11 minutes between energy pulses. The comparison that keeps forcing its way into your mind, and you hate this. You really do. Because it sounds sensational, is not to a natural comet breakup. It's to a controlled demolition. You've seen videos of buildings being demolished with precisely timed explosive charges. Load-bearing columns taken out in sequence, boom, boom, boom. The structure collapses in stages, each phase triggered at exactly the right moment for maximum effect. You shake your head. No, that's crazy thinking. You're exhausted. You're overwhelmed by what you just witnessed, and your brain is making connections that aren't there. This is a comet. It's made of ice and rock and organic compounds. It travelled through space for millions of years and happened to come close enough to our sun to get torn apart by thermal and tidal stress. The timing is coincidental. The pulses are probably rotational. Maybe the nucleus was tumbling, and we were seeing different faces catastrophically fail as they rotated toward the sun. But you can't explain the energy levels. Not with any model, you know. By 0200 UTC, observatories across the globe have captured enough data to start building a picture of what 3i/Atlas looks like now. And looks like is doing a lot of work in that sentence. Because what it looks like is a debris field, a rapidly expanding cloud of fragments, dust and gas spreading out along the object's original trajectory. Doctor. Naomi Rowe Gurney from NASA. Goddard posts high-resolution images from Hubble. The Space Telescope had been pre-positioned to observe the Perihelion passage. And the images are stunning. Where there used to be a single compact nucleus, there's now a diffuse cloud maybe 5,000 kilometers across and growing. You can see individual bright knots in the cloud larger fragments. Probably chunks of the original nucleus that are still somewhat intact. The largest piece appears to be maybe 200 meters across, about a quarter the size of the original object. But here's what makes you lean closer to your screen. The debris field isn't symmetric. When comets naturally fragment, the pieces tend to spread out in a relatively even pattern, following Keplerian orbits that don't differ much from the parent body. It looks organic, chaotic in a natural way. The 3i/Atlas debris field has structure. The fragments are clustered in distinct groups, almost like they were ejected in preferred directions. 3 main clusters. Actually, you count them on the Hubble image. 3 groups of fragments, corresponding to those 3 brightness pulses you observed. It's like it broke apart in stages, Sarah says, looking over your shoulder. Sequential fragmentation, or simultaneous fragmentation of 3 pre-existing pieces, you counter, trying to find the most natural explanation. If the nucleus had already cracked into 3 large fragments during those earlier outbursts, they might have been held together loosely until perihelion stress pulled them apart. Then why the energy pulses? If they just drifted apart, you wouldn't get those brightness spikes. She's right. Drifting apart is gentle. What you observed was violent. Each pulse released enough energy to vaporize tons of material, creating those intense emission lines. You need more data. You need trajectory information on those fragments, spectroscopic analysis of the debris cloud composition, thermal modelling of the energy release. You need time to think, to analyse, to compare with every other comet fragmentation event in the historical record. But even as you're planning your analysis, even as you're organising your thoughts into the structure of a research paper, that uneasy feeling persists. Because there's one more detail that doesn't fit. One more anomaly that you noticed during those frantic 8 minutes of observation but haven't fully processed yet. The timing of the explosion 0017 UTC on March 12th. That's not just close to perihelion. According to your orbital calculations, that's within 90 seconds of the exact moment of perihelion passage. The precise instant when 3I/Atlas was at its absolute closest point to the Sun. What are the odds that a natural fragmentation event would occur at that exact moment? Thermal stress builds gradually as an object approaches the Sun. Structural failures can happen anywhere along that approach. They should be somewhat random, clustered around perihelion but not pinpointed to it. But 3I/Atlas waited, held together through all those strange outbursts, through the building heat and stress of the approach, and then, at the mathematically perfect moment, at the instant of greatest drama, you might say it tore itself apart in 3 precisely timed pulses. And sitting there in the observatory, watching the debris field expand on your screen, you realise something that sends a chill down your spine. You have absolutely no idea what you just witnessed. So let's step back for a moment. Before we dive deeper into the mystery of why 3I/Atlas exploded the way it did, you need to understand what comets are supposed to do when they get close to the Sun. Because if you don't know the rules, you can't appreciate how thoroughly 3I/Atlas just broke them. Think of a comet as a time capsule from the early solar system, a dirty snowball, like I mentioned earlier, but that phrase doesn't really capture the complexity. A better description: imagine taking the mixture of water ice, frozen carbon dioxide, frozen methane, frozen ammonia, then mixing in dust, pebbles, organic compounds, and maybe some rocky chunks. Pack it all together loosely, not compressing it too much. What you get is something more like a cosmic dirt clod than a solid ice cube. Porous, fragile, held together by frozen volatiles and weak gravity. Now leave that dirt clod in your freezer for 4.6 billion years at temperatures around 40 Kelvin, that's negative 387 degrees Fahrenheit. So cold that even the atoms barely vibrate. That's what a comet experiences out in the distant reaches of space. Frozen solid, stable, dormant. Then something perturbs it. Maybe a passing star's gravity gives it a nudge. Maybe a planetary migration event in its home system kicks it out. Suddenly, it's falling toward a star, our Sun, in this case, and as it falls inward, something starts to happen. You know that feeling when you take ice cream out of the freezer on a hot summer day, how the surface starts to soften, gets a little wet, starts to drip. That's basically what happens to a comet, except instead of dripping, the ice turns directly from solid to gas, a process called sublimation. No liquid phase, straight from frozen to vapour. This is where comet behaviour gets interesting and, importantly, predictable. As the sun's radiation heats the surface and the ices begin to sublimate, water ice starts becoming active around 3 AU from the sun, that's roughly the distance of the asteroid belt. Closer in, around 2.5 AU, the sublimation accelerates. By the time a comet reaches 1 AU Earth's distance, it's typically producing thousands of kilograms of gas per second. That gas doesn't just disappear, it streams away from the comet, carrying dust particles with it. This creates the coma, that fuzzy cloud around the nucleus that makes comets look, Well, cometry. The solar wind then pushes this material back, creating the tail. Actually, two tails: a dust tail that follows the comet's orbit, and an ion tail that always points directly away from the sun, sculpted by the solar magnetic field. Here's the key part: this process is gradual and predictable. We have equations for this. The Whipple model, developed in the 1950s and refined over decades, describes how sublimation rates depend on solar distance, rotation rate, and composition. You can plug in the numbers and get pretty accurate predictions of how bright a comet should be at any given distance from the sun. Comet Hale-Bopp in 1997. We tracked it for months, watched it brighten exactly as predicted. Peak at magnitude minus 0.8, bright enough to see in broad daylight if you knew where to look, and then fade as it receded. Beautiful. Predictable. Physics working exactly as advertised. Comet Neowise in 2020, same thing. It brightened, developed a spectacular tail, put on a great show for Northern Hemisphere observers in July, then faded as it headed back out. The brightness curve matched theoretical predictions within a few percent. Textbook comet behaviour. Even when comets fragment, they usually do it in predictable ways. The thermal stress model, first developed by Zdenek Sekanina at JPL in the 1980s, explains it beautifully. As a comet approaches the sun, the surface heats up faster than the interior. This creates thermal gradients, stress fractures. If the nucleus already has cracks or weak points, and most do, from millions of years of cosmic ray bombardment and micrometeorite impacts, those weak points fail. The nucleus splits. The fragments separate gently, each continuing on a slightly different orbit. The energy involved in normal fragmentation is minimal. It's not explosive. There's no bang. The pieces just drift apart. Maybe you see a slight brightening as fresh. Previously buried ice gets exposed to sunlight and sublimates more actively. But we're talking about magnitude changes of 0.5 to 1. 0 spread over days or weeks. Comet C 2012 Eswana-son is actually a perfect case study. You remember I mentioned it earlier, the comet of the century, that disappointed everyone. Let's look at what actually happened to it in detail, because the contrast with 3 I/8less is important. ISON approached perihelion on November 28th, 2013, at a distance of just 1.2 million miles from the Sun's surface. That's insanely close, well within Mercury's orbit, passing through the solar corona itself. The Sun's heat was intense. ISON brightened significantly as it approached, reaching about magnitude 3.5 before perihelion. Everyone was excited. This was going to be spectacular. And then it wasn't. As ISON rounded the Sun, something happened. The nucleus began to break up. Observers watched in real time as the comet faded rapidly. By the time it emerged from behind the Sun, it was barely visible, just a diffuse cloud of debris. The brightening we expected never came. The great show never happened. ISON had essentially evaporated, torn apart by the combination of thermal stress and tidal forces. But here's the crucial detail: ISON's demise took hours and showed warning signs. The brightness didn't spike dramatically, it faded. The fragmentation was gradual. We watched the nucleus elongate, stretch, blur into a diffuse smear. It died slowly, not explosively. The energy balance made perfect sense. Sun heats comet. Ice sublimates, structure weakens. Gravity, which is already incredibly weak for such a small object, can no longer hold things together. And the whole thing just comes apart like a sandcastle in the rain. The total energy released by ISON's fragmentation, basically zero in explosive terms. It was entirely thermal, the Sun's radiation doing its work. No mysterious energy source. No unexplained brightness pulses. Just physics, sad and predictable. Compare that to what you just watched with 3I/Atlas. magnitude 8.7 to magnitude 2.8 in under 8 minutes. That's not gradual. That's not structure weakens and drifts apart. That's violent. That's explosive. The energy released during those 3 pulses was equivalent to detonating thousands of tons of TNT. Where did that energy come from? Let me put some numbers on this to make it concrete. When you analyse the photometric data, the brightness measurements, you can calculate the energy output. Each magnitude represents a brightness factor of about 2.5. So a 4 magnitude increase means the object became roughly 40 times brighter. Converting that to actual energy output, accounting for the distance and the surface area of the expanding debris cloud, you're looking at a total energy release on the order of 10 circumflex 14 joules. That's 100 trillion joules, the equivalent of about 24 kilotons of TNT. For comparison, the atomic bomb dropped on Hiroshima released about 63 trillion joules, roughly 5 times more energy than 3I/Atlas's explosion. Now, obviously, the mechanisms are completely different, but I want you to understand the scale here. This wasn't a gentle crumbling. This was a violent, energetic fragmentation event. Where does that energy come from in a comet? Sublimating ice doesn't release nearly enough energy. When water ice turns to vapour, it absorbs energy that's an endothermic process. It cools things down. It doesn't heat them up. You can't power an explosion with sublimation. Could it be chemical energy, some kind of exotic, volatile compound that reacts violently when heated possible? But we studied comet compositions extensively. They're mostly water ice, with some carbon monoxide, carbon dioxide, methane, ammonia, nothing explosive. Nothing that would detonate with that kind of energy release. Could it be rotational energy if the comet was spinning rapidly and suddenly broke apart? The rotational energy would be converted to kinetic energy of the fragments. But 3I/Atlas's rotation period was about 8.3 hours, pretty slow. The rotational energy available from a 500-metre object spinning that slowly is nowhere near enough to explain what you've observed. Tidal energy from the sun's gravity. No, at 0.65 AU, the tidal forces are minimal. You'd need to be much closer like ISON's 1.2 million miles to get significant tidal stress. And even then, tidal forces pull things apart. They don't create explosive energy releases. So where did the energy come from? What natural mechanism takes a comet and turns it into something that explodes with nuclear-scale energy at the precise moment of perihelion in 3 distinct, evenly spaced pulses? This is the question that's keeping you awake now, hours after the event. You've run through every conventional explanation you know, and none of them work. The physics doesn't add up. The energy budget is wrong. The timing is too precise. And as the sun rises outside your observatory, painting the sky in soft morning colours, you realise that you're going to have to start considering unconventional explanations. Explanations that make you uncomfortable. Explanations that might get you laughed at in peer review. But what if the conventional explanations are simply insufficient? What if 3I/Atlas is trying to teach us that our models built on observations of local comets that formed in our solar system don't apply to visitors from beyond? You've compiled a list, sitting at your desk 3 days after the explosion, coffee mug number 5 at your elbow. You've written down every anomaly, every detail that doesn't fit the standard comet model. The list is longer than you'd like. Much longer. Let's go through it together, because I want you to feel what you're feeling right now, that growing sense that you're looking at something that shouldn't exist according to everything we know about comets. Anomaly 1. The timing. Perihelion occurred at 00:1723 UTC. The first brightness pulse began at 00:1731 8 seconds later. 8 seconds. That's not around perihelion or near perihelion. That's at perihelion, within the margin of error of your orbital calculations. The probability of a random structural failure occurring at that exact moment, you've run the statistics. It's less than 1%. Comets can fragment anywhere along their approach, over a window of hours or days. But 3i/Atlas waited for the mathematically perfect moment. It's like watching someone wait until the exact stroke of midnight to pop a champagne bottle. Nature doesn't usually care about precise timing. Anomaly 2. The triple pulse. 11 minutes between the first and second brightness peaks. 10 minutes and 40 seconds between the second and third. Those aren't random intervals. If different parts of the nucleus were failing independently due to thermal stress, you'd expect chaotic timing, one failure triggering another through mechanical stress, creating a cascade with irregular spacing, but 3i/Atlas pulsed like a heartbeat, regular, measured. You keep coming back to that word measured. Doctor. Cheng Jiang from Lowell Observatory posted an analysis on Arcsev 2 days after the event. The periodicity of the brightness pulses does not correlate with the known rotation period of 8.3 hours. The spacing suggests either a previously unknown structural organization within the nucleus or a non-rotational mechanism for sequential fragmentation. Translation, he has no idea either. Anomaly 3, the energy signature. You've calculated and recalculated the energy output, 24 kilotons equivalent across all 3 pulses. Where did it come from? You've considered every energy source available to a comet gravitational potential, energy minimal. The pieces were barely held together by gravity in the first place. Rotational kinetic energy insufficient by 2 orders of magnitude. Chemical energy from exotic volatiles. Nothing in the spectroscopic data supports highly energetic compounds. Thermal energy from solar heating. That's energy input, not output. It can cause structural failure, but it can't create an explosion. The math doesn't work. It's like finding a car that travelled 500 miles on a gallon of gas. Something's wrong with either your measurements or your understanding of the system. And you're pretty confident about your measurements. Anomaly 4, the debris pattern. Remember those Hubble images showing 3 distinct fragment clusters? You've been analysing the trajectories of those fragments over the past 72 hours. Most of the pieces are following orbits close to the original path that's expected. When something breaks apart, the fragments inherit the parent object's velocity plus whatever small push they received from the fragmentation event. But some of the fragments are moving wrong. Specifically, there's a cluster of smaller pieces, each maybe 10 to 30 meters across, that are moving retrograde relative to the main debris field. They're travelling at about 2.3 kilometers per second in a direction that's 47 degrees off from where they should be going. To achieve that trajectory, they would have needed to be ejected with significant force at a very specific angle. That's possible in an explosion. Sure, but here's the weird part. All the retrograde fragments are moving in roughly the same direction, like they were ejected from a single point source. That's not how random explosions work. When something explodes chaotically, debris goes everywhere. This looks almost aimed. Anomaly 5. The pre-explosion behaviour. You've gone back through all your observation logs from February and early March. Those random outbursts that seemed so puzzling at the time. You've plotted them on a timeline. 17 outbursts total between February 18th and March 10th. The frequency increased as 3i/Atlas approached the sun that's normal, expected. But the intensity didn't correlate with solar distance the way it should. The strongest outburst happened on February 24th, when the object was still 0.92 AU from the sun. After that, the outbursts were actually weaker on average, even though the object was getting closer and should have been heating up more. It's like the object spent its energy budget early, then went quiet, then exploded. Dr. Elliot Young from Southwest Research Institute noted in a conference call, The outburst pattern suggests either an inhomogeneous composition with pockets of high volatile material that were exhausted early, or a different mechanism entirely. We're looking at something unprecedented. Anomaly 6. The spectroscopic weirdness. Sarah has been obsessing over the spectra from the explosion. The emission lines during those brightness pulses showed elements you'd expect: sodium, potassium, calcium, iron. Those are all normal components of rocky material being vaporized. But the ratios are wrong. There's too much sodium relative to everything else. And there's that mysterious feature at 388 nanometers that still hasn't been definitively identified. It could be CN, Sarah says, referring to cyanide compounds. But if it is, the abundance is off the charts, way higher than any comet we've ever observed. Could 3I/Atlas have formed in a chemical environment totally unlike our solar system, a star system with different elemental abundances? Maybe a younger system richer in heavy elements possible. But that doesn't explain the explosion, and anomaly 7, the missing tail. This one bothers you more than you like to admit. In all your observations leading up to Perihelion, 3I/Atlas never developed proper tail. It had a weak coma, barely visible, but nothing like the spectacular tails of normal comets at similar distances. It's as if the surface was sealed somehow, preventing the normal sublimation of ice. But if the surface was sealed, what were those outbursts? Something was venting. Something was releasing gas and dust, just not in the continuous, predictable way that comets usually do. The more you think about it, the more it feels like 3I/Atlas was holding something in, building pressure, maybe waiting, and then at perihelion, everything released at once. Except comets don't have pressure relief valves. They're not sealed containers. They're porous, loosely packed rubble piles. Pressure can't build up because there's nowhere for it to build. Gas just percolates through the porous structure and escapes gradually. Unless the structure wasn't porous, unless it was sealed. But what natural process creates a sealed comet? Anomaly 8, the rotation rate change? This is new data, just came in this morning. Dr. Beatrice Mueller from ESA analysed high-cadence photometry from the days before perihelion and found something remarkable: 3I/Atlas's rotation period was changing. It started at 8.3 hours on March 1st, but by March 10th it had slowed to 8.7 hours. Rotation rates can change in comets. Outgassing can create torques, like tiny rocket engines, that spin the nucleus up or down. But 3I/Atlas was slowing down, and it was doing so steadily, almost linearly. Over 10 days it lost about 4.8% of its rotational velocity. That's not random outgassing. That's consistent torque being applied in a specific direction over an extended period. Dr. Muller wrote in her report, the deceleration profile suggests either a sustained asymmetric outgassing pattern, which is unusual, or an internal mass redistribution, which is unprecedented for objects of this size. You stare at that line for a long time. Internal mass redistribution. What could cause that ice migrating from one side to another as the sun heats it? Maybe. But the math suggests you'd need to move about 15% of the object's total mass from one hemisphere to another to create the observed rotation change. That's not subtle. That's not a little bit of ice sublimating and redepositing. That's something major happening inside. So here's where you are 8 anomalies, each one individually explainable if you stretch your assumptions a bit, but together they paint a picture that doesn't make sense. It's like a jigsaw puzzle where all the pieces are slightly the wrong shape. You can force them together if you try hard enough, but the final image looks distorted, wrong. You're a scientist. You're trained to find natural explanations, to apply Occam's razor, to prefer simple answers over complicated ones. And every instinct you have is screaming at you to find a way to make this fit into conventional comet physics. But what if it doesn't fit? What if you're trying to force a square peg into a round hole? What if the reason nothing makes sense is because you're asking the wrong question? You're not asking, how did this comet explode anymore? The question evolving in your mind, the one you're almost afraid to write down, is simpler and more disturbing. Was 3I/Atlas actually a comet at all? Before you let your mind wander into truly exotic territory, you need to do your due diligence. You're a scientist, not a conspiracy theorist, so let's systematically work through every natural explanation for what happened to 3I/Atlas. Let's give conventional physics every possible chance to explain this event, because if there's a mundane answer hiding in the data, you need to find it before you start suggesting anything more. Unusual. Theory 1. Catastrophic thermal stress breakup. This is the default explanation. It's what everyone's first instinct suggests. 3I/Atlas spent millions of years in the deep freeze of interstellar space, then suddenly got blasted by intense solar radiation at perihelion. The thermal shock was too much. The structure failed. End of story. You sit down with the thermal models. The sun's radiation at 0.65 AU delivers about 300-400 watts per square meter to the surface, roughly 2.4 times what Earth receives. For an object coming from near absolute zero, that's significant. You calculate the temperature gradient, the sunlit surface could reach 400 Kelvin, while material just a few meters below the surface remains frozen at maybe 100 Kelvin. That's a 300-degree temperature difference over a very short distance. Temperature gradients create stress. The outer layers want to expand while the inner layers stay contracted. If the material is brittle and after millions of years of cosmic ray bombardment, it probably is cracks form. The structure weakens, eventually catastrophic failure. Okay, that works for explaining why it broke apart, but does it explain how you run the calculations? The mechanical energy stored in thermal stress, even with extreme gradients, is maybe 10 circumflex 11 joules, 100 billion joules. That sounds like a lot until you remember that the explosion released 10 circumflex 14 joules. You're short by a factor of 1,000. Maybe there was subsurface ice that flash boiled, your colleague suggests during a video conference that afternoon. Pressure building up in sealed cavities, then explosive decompression. You've thought of that. It's actually a well-known mechanism comets can develop sealed ice layers near the surface that trap gases beneath. When those layers rupture, you get sudden outbursts. It's been observed on comets like Hartley 2 and 67P. But here's the problem: those outbursts are localized. They're jets. You see them as bright spots on the surface, shooting material into space from specific locations. They don't cause the entire nucleus to explode simultaneously. And they definitely don't produce 3 separate, evenly timed pulses. You run simulations anyway, modelling different configurations of subsurface voids and sealed layers. In your best case scenario, which involves some pretty generous assumptions about cavity sizes and gas pressures, you can maybe account for 10 circumflex 12 joules of energy. Still 100 times too low. Thermal stress insufficient. Theory 2. Hypervolatile compound detonation. What if 3I/Atlas contained something really exotic? Something we don't normally see in solar system comets. The object came from another star system. After all, maybe it formed in a chemical environment rich in unstable compounds. There are known chemicals that are both cryogenic and explosive. Ozone, for instance, can exist as a solid at low temperatures and decomposes explosively when disturbed. Or nitrogen compounds, some forms of solid nitrogen can be shock sensitive. Or maybe some complex organic molecule we've never encountered. Something that's stable at 40 Kelvin but detonates when warmed. You dive into the spectroscopic data with renewed focus. If 3I/Atlas contained hypervolatile compounds in significant quantities, you should see evidence in the emission spectra. unusual molecular bands, unexpected element ratios. Sarah sends you her detailed analysis. The spectra show all the normal stuff: CN cyanide, C2 diatomic carbon, O hydroxyl radicals, sodium, iron. The sodium abundance is high, yes, but not impossibly so. That mystery feature at 388 nanometers could potentially be attributed to CH plus methylidine cation, though it's a bit of a stretch. Nothing screams exotic explosive compounds. More importantly, the energy density is wrong. Even if you packed 3I/Atlas entirely full of the most energetic chemical explosives, we know stuff like octanitrocubane, which releases about 15 megajoules per kilogram, you'd still come up short. A 500-meter spherical object with a reasonable density of 500 kilograms per cubic meter has a mass of about 1.3 x 10 circumflex 11 kilograms. If 10% of that mass was exotic explosives, an absurdly high percentage, you'd get maybe 2x10 circumflex 14 joules. Okay, that's actually in the right ballpark. Except where did the trigger come from? Explosives don't just decide to detonate on their own. They need an initiation event, a shock, a spark, something. And why 3 separate detonations with precise timing? You could argue that the thermal shock triggered the first detonation, which triggered the second, which triggered the third. But that requires the explosive material to be organised in separate pockets with specific spacing. How does nature create that kind of internal structure? The more you think about it, the less sense it makes. And honestly, if 3I/Atlas was full of explosives, you should have seen evidence during those February outbursts. Small detonations, test firings, if you want to think of it that way. The spectroscopic signatures would have been distinctive. Hypervolatile detonation implausible. Theory 3. Spin-up and rotational breakup. Here's an idea. What if 3I/Atlas was spinning up as it approached the Sun? Comets can experience torques from asymmetric outgassing jets of material shooting off preferentially in one direction, acting like tiny rocket thrusters. If those torques accumulated over weeks, the rotation rate could increase dramatically. Eventually, centrifugal forces overcome the object's self-gravity, and it flies apart. This has actually happened. Comet 332P/Ikea Murakami spun itself to pieces in 2016. Astronomers watched it rotate faster and faster until fragments started peeling off. It was spectacular and entirely natural. You pull up the rotation data again. 8.3 hours on March 1st, 8.7 hours on March 10th. Wait, that's spinning down, not up. The object was losing rotational velocity as it approached perihelion. That's the opposite of what this theory requires. Could the data be wrong? You check the observations. Multiple independent measurements from different observatories. No, the deceleration is real. Could there be some weird scenario where the object was spinning down right up until the last moment, then suddenly spun up catastrophically in the final hours that would require a massive, sudden torque? Where would that come from? Rotational breakup contradicted by observations. Theory 4. Pre-existing fractures and tidal stress. Maybe 3I/Atlas was already broken before perihelion. Those February outbursts could have fractured the nucleus into several large pieces held together by minimal strength. Then, as the object passed through perihelion, subtle tidal forces from the Sun's gravity, even though they're small at 0.65 AU, were enough to pull the pieces apart. Once separated, each piece would brighten independently as fresh ice became exposed. That could explain the 3 pulses, 3 major fragments separating sequentially. You model this scenario carefully. The tidal force at 0.65 AU on a 500-meter object is about 0.00001 times the object's own surface gravity. That's minuscule. To pull apart pieces that are already fractured, you need essentially 0 tensile strength holding them together, We're talking about fragments just barely touching, held by nothing but the faintest whisper of gravitational attraction. Possible, yes. You can construct a scenario where the nucleus is so fragmented and so weakly bound that tidal forces at perihelion are sufficient to separate the pieces. But this doesn't explain the energy release. Pieces drifting apart gently don't release 10 circumflex 14 joules. You'd see a brightness increase from exposed ice, and sure, but gradual and modest, not explosive pulses, and it definitely doesn't explain those retrograde fragments moving at 2.3 kilometers per s in a preferential direction. Those fragments were ejected with significant force, not gently separated. Tidal fragmentation explains some features, fails on energy budget. Theory 5, impact event. Here's a wildcard. What if 3I/Atlas hit something interstellar space isn't completely empty? There are dust grains, maybe small rocks. If 3I/Atlas struck a meteoroid at high relative velocity right around perihelion, the impact energy could have shattered the nucleus. You calculate the odds. The space density of meteoroids in the inner solar system is roughly 10 circumflex, 20 kilograms per cubic meter. The probability of hitting something large enough to matter during the few hours around perihelion? Essentially zero. You're talking lottery winner struck by lightning on their birthday levels of improbability. And anyway, an impact would produce a single event, not 3 pulses, and the impact would need to be absurdly well timed to occur exactly at perihelion. Impact statistically impossible. You lean back in your chair, rubbing your eyes. It's late. You've been at this for 16 hours straight. 5 natural explanations, each one failing in a different way. None of them work. Not completely. You can explain parts of what happened, but not the whole thing. Not the precise timing, not the energy release, not the structured debris pattern, not the 3 pulses. What does it mean when every conventional explanation fails? Either your understanding of the observations is wrong, but multiple independent measurements confirm the same things, or your understanding of the physics is incomplete. There's a third option, one that's been lurking at the edge of your consciousness since you watched those brightness curves spike on your screen. Maybe what happened to 3I/Atlas wasn't entirely natural. Maybe, and I know how this sounds, maybe something about this object was designed, and that thought, as uncomfortable as it makes you, is about to lead you down a path that will challenge everything you thought you knew about what's possible in our universe. Okay, deep breath. Let's talk about the thing that most scientists won't say out loud at conferences. The hypothesis that gets you weird looks in the faculty lounge. The idea that can end careers if you push it too hard without evidence. Let's talk about the possibility, and I want to be very careful with my words here, that 3I/Atlas might not have been a natural object. I can almost feel some of you tensing up. Here we go with the alien stuff. And I get it, I really do. The moment you suggest that something in space might be artificial, you've crossed a line in many people's minds. You've gone from serious scientist to that guy with the tinfoil hat on the History Channel. But here's the thing. The scientific method doesn't care about what makes us uncomfortable. It cares about evidence and explanations. And when all the natural explanations fail, genuinely fail, not just we haven't figured it out yet, but the physics literally doesn't work, then you have an obligation to consider alternatives, even uncomfortable ones. So let's do this properly. Let's look at 3I/Atlas through the lens of the artificial hypothesis. Not because we want it to be true, but because we need to see if it fits the data better than the natural explanations. And let's be clear, I'm not claiming this is what happened. I'm exploring whether it could explain what we observed, the Oumuamua precedent. You're not the first person to wonder about interstellar visitors being artificial. That honour goes to Professor Avi Loeb at Harvard, and the object in question was Oumuamua. Remember that one back in 2017, that strange cigar-shaped thing that tumbled through our solar system and then accelerated on its way out. The acceleration was the key issue. Oumuamua was moving faster than gravity alone could explain. Something was pushing it, the natural explanation outgassing, like a comet. But there was no visible coma, no tail, no gas detected. So where was the push coming from? Loeb, along with his postdoc Shmuel Bialy, published a paper in the Astrophysical Journal Letters in November 2018 that caused an absolute firestorm. They suggested carefully, with proper scientific hedging, that Oumuamua's acceleration could be explained if it were a light sail. A thin reflective sheet pushed by solar radiation pressure. In other words, artificial. The backlash was immediate and intense. Other astronomers published rebuttals. It's outgassing we just can't detect. It's made of hydrogen ice. It's a cosmic dust bunny. Anything but artificial. Loeb was called sensationalist, accused of doing bad science, of seeking publicity. But here's what's interesting. None of the natural explanations for Oumuamua are completely satisfying either. They all require a special pleading, unusual assumptions. The hydrogen ice hypothesis requires Oumuamua to be made of a substance we've never observed in nature. The undetectable outgassing requires us to believe we just happened to miss all the evidence. Loeb's point, and it's a good one, is that we shouldn't dismiss the artificial hypothesis just because it makes us uncomfortable. We should evaluate it on the same playing field as natural hypotheses. Does it fit the data? Is it testable? Does it make predictions? So let's apply that framework to 3I/Atlas. If it were artificial, the deorbiting scenario. Imagine, just for a moment, that 3I/Atlas wasn't a comet. Imagine it was a probe, a spacecraft, sent from another civilization millions of years ago. It's travelled through interstellar space for eons, and now it's approaching our sun on a hyperbolic orbit that will slingshot it back out into the galaxy. But maybe the mission is over. Maybe whatever it came here to do is done. Maybe its systems are failing after millions of years. Or maybe it was always designed to be a one-way trip, and now it needs to dispose of itself. What would you do? You deorbit. You destroy the spacecraft in a way that prevents it from potentially contaminating another system, or being recovered by anyone who might find it. And where's the most efficient place to do that in a solar system at perihelion? The closest point to the star, maximum thermal stress, maximum tidal forces, the perfect place to ensure complete destruction. Suddenly, that precise timing doesn't look coincidental anymore. The object waited until the exact moment of perihelion to initiate its self-destruct sequence. Waited until it was at the mathematically optimal point for ensuring no large pieces survive. Those 3 pulses, stages of demolition. Primary charges, secondary charges, final breakup. Timed precisely to ensure complete fragmentation. 11-minute intervals, because that's how long it takes between detonation sequences to verify that each stage was successful. The energy release, not thermal stress or chemical reactions, explosive charges, or something more exotic. A civilization capable of interstellar travel probably has energy storage technologies we can't imagine. Those 24 kilotons of energy would be trivial for any sufficiently advanced technology. The retrograde fragments moving at 2.3 km per s in a specific direction intentionally ejected debris, maybe sensor packages, maybe data storage units, thrown clear of the main destruction to potentially be recovered later by whoever sent the probe. Does this sound crazy? Absolutely. But does it fit the observations better than thermal stress or hypervolatile compounds? You tell me. The quiet approach problem. Here's something that bothers you about the artificial hypothesis. Though, if 3I/Atlas were a probe, why was it so quiet for so long? It was discovered in January 2024, 14 months of observation before the explosion. In all that time, it looked mostly like a comet. It had those weird outbursts, sure, but nothing that screamed artificial. No radio transmissions detected, no optical signals, no evidence of active propulsion. If something wanted to be noticed, if it wanted to communicate, you'd think it would be more obvious about it. Right, unless. What if being noticed was the last thing it wanted? What if 3I/Atlas was designed to look natural, a stealth probe, disguised as a comet, able to pass through star systems without triggering alarm, observe without being observed, study without being studied? The outburst could have been thruster firings, small course corrections masked as natural comet activity. That rotation rate change of the object slowing down over 10 days could have been attitude adjustment, reorienting for the final perihelion passage. And then, mission complete, it destroys itself, leaves nothing behind but a debris field that looks almost like a normal comet fragmentation. Almost, except for those little anomalies that someone like you, someone paying very close attention, might notice. The scientific caution. Now, before you start thinking I've gone completely off the rails, let me pump the brakes hard. Everything I just described is speculation. Fun speculation. Maybe even logical speculation, but speculation nonetheless. We have zero direct evidence that 3I/Atlas was artificial. Zero. No recovered fragments with circuit boards or metal alloys. No radio signals. No mathematical patterns in the outburst timing. No inscription saying made on Zeta Reticuli. Nothing but anomalous data that doesn't quite fit natural models. And here's the crucial thing about science. Extraordinary claims require extraordinary evidence. Carl Sagan said that, and he was right. The claim that 3I/Atlas was an alien probe is about as extraordinary as claims get. The evidence we have, timing anomalies, energy budget problems, weird fragment trajectories, is suggestive. Sure, but it's not extraordinary. Not yet Dr. Michelle Bannister, who's been studying 3I/Atlas since its discovery, said in a recent interview, "We need to be very careful about jumping to artificial explanations before we've exhausted all natural possibilities. The history of astronomy is full of mysteries that turned out to have mundane explanations once we understood the physics better." She's right. Remember pulsars when they were first discovered in 1967? The regular radio pulses were so precise that astronomers jokingly called them LGM 1 Little Green Men 1. Turned out to be rotating neutron stars, as natural, just exotic. Quasars once thought to be possibly artificial because nothing natural could be that energetic. Turned out to be supermassive black holes actively feeding. Natural, just extreme. The lesson: don't assume aliens when you haven't ruled out physics you don't understand yet. The middle path. So, where does that leave you? Sitting in your observatory with data that doesn't make sense. Somewhere in the middle, probably. Acknowledging that the natural explanations have serious problems, but also acknowledging that the artificial explanation requires a massive leap. Maybe 3I/Atlas was a natural object, but formed under conditions so different from our solar system that our models simply don't apply. Maybe interstellar comets are just weird in ways we haven't figured out yet because we've only seen 3 of them. Maybe there's physics happening inside these objects that we don't understand, exotic ice phases, pressure-driven crystallization changes. Who knows? Or maybe, just maybe sometimes, when something looks artificial, acts artificial, and defies natural explanation, we should at least seriously consider the possibility that it is artificial. The truth is, you might never know for certain, and that uncertainty, that unknowability, is going to haunt this observation forever. But whether 3I/Atlas was a comet that exploded in a really weird way, or something much stranger, one thing is absolutely certain: we need to be watching. Because if there are more visitors coming, the next one might give us the answers this one took to its explosive grave. So what happens now? You can't just watch an interstellar object explode in the most mysterious way possible and then go back to cataloguing asteroid orbits. The explosion of 3/Atlas isn't an ending, it's a beginning. The beginning of one of the most intensive astronomical investigations in modern history. It's been 3 weeks since Perihelion. You're now part of a global collaboration involving 47 institutions across 18 countries. The Discord channel that had 247 people on explosion night now has over 800 researchers. There are 7 working groups analysing different aspects of the event. You're on the debris dynamics team, tracking where all those fragments are going. And here's what you're learning. The debris field is not behaving the way anyone predicted. The expanding mystery. By now, the fragments have spread across a region of space about 2 million kilometres wide, roughly 5 times the distance from Earth to the Moon. That might sound enormous, but in astronomical terms, it's still relatively compact. You can fit the entire debris field inside an area smaller than the Sun. Your team has identified 143 distinct fragments large enough to track individually. The biggest piece is that 200-metre chunk visible in the Hubble images. The smallest trackable pieces are maybe 5 metres across, basically boulders. Between those extremes, you got everything from car-sized rocks to apartment building-sized chunks. Each fragment is on its own trajectory now, still following hyperbolic orbits that will carry them back into interstellar space. But they're spreading out, diverging like a shotgun blast. Some are travelling faster than the original object, some slower. The velocity differences are subtle, we're talking tens of meters per second, but over months and years, those small differences will scatter the debris across light years of space. Dr. Marco Micheli from ESA's Near-Earth Object Coordination Center is leading the effort to catalogue every fragment's orbit. He posted an update yesterday. We're seeing velocity dispersions up to 180 meters per second relative to the parent body's trajectory. This is consistent with energetic fragmentation, but exceeds typical comet breakup velocities by a factor of 3 to 5. Translation: the pieces are moving faster than they should be if this were a gentle thermal breakup. They were thrown outward with significant force. The JWST deep dive. The James Webb Space Telescope has been absolutely crucial to this investigation. JWST's infrared capabilities let it see things that optical telescopes miss specifically. The thermal emission from dust and small fragments that are too faint to see in visible light. On March 25th, 2 weeks post-explosion, JWST conducted a 12-hour deep observation of the debris field. The data came back yesterday, and it's fascinating. The field is filled with dust, microscopic particles that glow in infrared as they absorb sunlight and re-radiate it as heat. That's normal for comet fragmentations. What's not normal is the distribution. Dr. Stephanie Millam from NASA Goddard, who's analysing the JWST spectroscopy, found something unexpected. The dust composition varies significantly across the debris field. The dust near those 3 main fragment clusters shows different spectroscopic signatures. One cluster is rich in silicates rocky material. Another shows organic compounds, carbon-based molecules. The third shows what might be water ice particles. It's like the object had distinct chemical zones. Dr. Milam explained in a team meeting. Morganunda's differentiated internal structure. We don't typically see that in comets, which are usually fairly homogeneous mixtures. Differentiation means different materials separated somehow, denser stuff sinking to the centre, lighter stuff rising to the surface. That happens in planets because they're big enough to melt and allow materials to separate by density. But a 500-metre comet, no way. Not enough gravity, not enough internal heat. It should be a uniform mix of whatever materials it formed from, unless it wasn't formed naturally, unless it was built with specific materials in specific locations for specific purposes. But let's not jump to that conclusion yet. The amateur contribution. Here's something beautiful that's come out of this event amateur astronomers around the world have mobilised to help track the debris. There are probably 200 backyard telescopes pointed at the 3/8 debris field on any given night, from California to Australia to South Africa. An amateur astronomer in Arizona named Tom Masterson captured one of the retrograde fragments on March 18th. He's got a 14-inch telescope in his backyard and was specifically searching for unusual trajectories based on your team's predictions. His observation helped refine the orbit of fragment R17. That's what you're calling the retrograde pieces. R for retrograde, numbered in order of discovery. Fragment R17 is travelling at 2.4 km per s at an angle 52 degrees off from the main debris field. If you trace its trajectory backwards to the moment of explosion, it originated from the second brightness pulse, the middle detonation. And if you trace it forwards, it's going to exit the solar system in a completely different direction than the main debris field. In about 40,000 years, it'll be roughly 3 light years away from where the largest fragment will be. Why does that matter? Because if you wanted to scatter pieces of something across the galaxy to maximise the chances of at least one fragment being found, eventually, this is exactly how you'd do it. You'd explode it with fragments going in different directions, at different velocities, spreading the debris across as much space as possible. Or maybe it's just random fragmentation mechanics creating random trajectories, and you're seeing patterns that aren't there because your brain is desperate to make sense of chaos. That's also possible. The ground-based campaign back on Earth. Every major observatory with the right instruments has dedicated time to 3/Atlas follow-up. The Atacama Large Millimeter Array ALMA in Chile has been mapping the molecular emissions from the debris. They detected carbon monoxide, formaldehyde, methanol, and complex organic molecules, basically the same stuff we see in normal comets. But the abundances are strange. There's too much methanol relative to water. The CO-CO2 ratio is off. It's like looking at a recipe where all the ingredients are correct, but the proportions are wrong. You can still make the dish, but it's going to taste weird. Every interstellar object is going to be different. Dr. Alan Fitzsimmons points out in a published analysis. They formed in different stellar environments, different protoplanetary disks. We shouldn't expect them to match solar system compositions. 3/Atlas's chemistry might be perfectly normal for wherever it came from. That's fair. That's the scientist in him being properly cautious. But even he admits the composition is highly unusual and warrants further investigation. The planetary defense angle. Here's something that's keeping NASA up at night. What if something like 3/Atlas was heading for Earth? Not just passing through the solar system, but actually on a collision course. How would we handle that? The explosion of 3/Atlas has triggered urgent discussions at the Planetary Defense Coordination Office. Dr. Lindley Johnson, NASA's Planetary Defense Officer, convened an emergency working group to study the implications. The problem is, everything we know about deflecting asteroids assumes they're natural objects made of rock or ice. Following predictable physics, you can nudge them with kinetic impactors like the DART mission demonstrated. You can use gravity tractors. You have options. But what if the object isn't natural? What if it's designed to resist deflection? What if it has propulsion, active guidance? Or worst case, what if it's deliberately targeting Earth and can course correct after you try to push it away? We need to prepare for scenarios beyond natural impacts. Dr. Johnson said in a closed-door briefing that was later leaked to the press. The 3/Atlas event demonstrates that interstellar objects can exhibit behaviours we don't fully understand. Whether natural or artificial, that's a knowledge gap we need to close. The meeting sparked a new initiative, the Interstellar Object Rapid Response Protocol. The goal is to have plans in place for quickly characterizing any future interstellar visitor, determining its trajectory with high precision, and if necessary responding to it as a potential threat. They're calling it IORP, pronounced IORP. And you've been asked to serve as a scientific advisor. The long wait for answers. The frustrating reality is that most of the questions about 3I/8LAS won't be answered quickly. Analysing the debris will take years. Understanding the chemistry will require laboratory work with analogues, trying to recreate the observed compositions under different formation scenarios. Modelling the explosion dynamics will require sophisticated computer simulations that might take months to run. And some questions might never be answered at all. You'll probably never know for certain where 3I/Atlas came from, which star system, which protoplanetary disk. You'll probably never recover a physical sample to analyse in a lab. The object is too far away now, moving too fast, the fragments too small and too scattered. But you keep working because that's what scientists do. You gather data, you build models, you test hypotheses, you eliminate possibilities until, hopefully, you're left with an answer that makes sense. And while you're doing that work, cataloguing fragments and running simulations and debating interpretations at 2 a.m. in Discord channels, there's another question lurking in the background. A bigger question. A question that makes the mystery of 3I/Atlas feel almost small by comparison. How many more are out there? And what will the next one teach us? Let me tell you what keeps you staring at the ceiling at night. Is not the unanswered questions about 3I/8LAS, though. Those are certainly keeping you busy during the day. It's something bigger. Something that the explosion forced you to confront in a way you'd been avoiding for your entire career. The universe is stranger than we think. And maybe, just maybe, it's stranger than we can think. The history of being wrong. Here's a humbling truth about astronomy. We've been spectacularly wrong about fundamental things, repeatedly, throughout history. Not because astronomers were stupid, but because the universe kept presenting us with phenomena that broke our models of what was possible. In 1054 AD, Chinese astronomers recorded a guest star that appeared in the constellation Taurus, bright enough to see in daylight for 23 days. European astronomers largely ignored it because the prevailing belief was that the heavens were perfect and unchanging. Stars didn't just appear, that would be absurd. Except it happened anyway. We now know it was a supernova, the explosion of a massive star. The expanding remnant is still visible today as the Crab Nebula. In 1781, William Herschel discovered Uranus and insisted it was a comet because planets didn't just get discovered. We'd known about the 5 visible planets since ancient times. The idea that there might be more seemed impossible. He was wrong. It was a planet. The solar system was bigger than we thought. In 1920, there was a famous debate between astronomers Harlow Shapley and Heber Curtis about the nature of spiral nebulae. Were they gas clouds within our Milky Way, or were they separate galaxies, entire islands of stars beyond our own? Shapley argued for gas clouds because separate galaxies would be so distant, so enormous, that it seemed ridiculous. Curtis argued for separate galaxies. Curtis was right. The universe was vastly larger than anyone had imagined. Not millions of stars, but hundreds of billions of galaxies, each containing hundreds of billions of stars. In 1967, Jocelyn Bell discovered pulsars radio sources that pulsed with clockwork precision, some ticking hundreds of times per second. The regularity was so perfect that it seemed artificial. Her supervisor, Anthony Hewish, half-jokingly named the first one LGM-1 for Little Green Men. The scientific consensus was that nothing natural could pulse that regularly. They were wrong. Pulsars are rotating neutron stars, city-sized objects spinning at incredible speeds. their lighthouse beam radiation sweeping across space with metronomic precision. Nature can be that regular. Nature can be that precise. Do you see the pattern throughout history? Whenever we've declared something impossible or too strange to be natural, the universe has delighted in proving us wrong. Not always in the direction we expected. Sometimes things are natural when they look artificial. Sometimes they're weirder than either option. The paradigm 3, I/Atlas, forces us to consider the explosion of 3 I/Atlas sits at an uncomfortable intersection. It's strange enough that natural explanations struggle, but not strange enough that we can definitively say it's artificial. It exists in that maddening grey zone where both interpretations seem simultaneously reasonable and inadequate. But here's what the event really represents: proof that interstellar objects are not just theoretical curiosities, they're real, they're detectable, and they're teaching us that the space between stars is more active, more interesting than we gave it credit for. Think about what we've learned in just 8 years. 3 confirmed interstellar visitors, 3 wildly different objects. Oumuamua with its strange acceleration and tumbling elongated shape, Borisov with its surprisingly normal comet behaviour, and now 3 I/Atlas with its explosive, energetic demise. If these 3 objects are representative of what's out there, and that's a big if, then interstellar space is filled with incredible diversity. Dr. Amaya Moreau-Martin from the Space Telescope Science Institute has been modelling the population of interstellar objects based on our detections. Her latest paper, published just last week, suggests there could be 10,000 Oumuamua-sized interstellar objects inside Neptune's orbit at any given moment. Most too faint to detect. Most pass through without getting close enough to the sun to be interesting, but they're there. A whole hidden population of cosmic wanderers drifting through our neighbourhood on their way to somewhere else. That number 10,000 changes everything. It means the galaxy is thoroughly mixed. Objects ejected from one star system eventually wander into others. Material spreads. Compositions diversify. And if objects can travel between stars naturally, through purely gravitational means, then what else can the implications for life? Let's talk about panspermia. It's the idea that life, or at least the building blocks of life, can spread between star systems via comets and asteroids. It's been around since the 1800s, proposed by various scientists including Lord Kelvin and Hermann von Helmholtz, and it's never been fully accepted because it seemed too difficult, too unlikely. But 3 I/Atlas changes the calculation. If there are thousands of interstellar objects constantly flowing through our solar system, and if our solar system is constantly ejecting objects into interstellar space, then the galaxy is more connected than we thought. Material exchange between star systems isn't a rare event. It's constant. Slow, sure, but constant. Complex organic molecules have been detected on 3 I/Atlas. We see them in the spectroscopy. Amino acid precursors, the building blocks that can lead to the proteins necessary for life. If those molecules survived the explosion, and some fragments certainly got thrown clear with minimal heating, then right now, there are pieces of 3 I/Atlas carrying complex organics back into interstellar space, where they'll drift for millions of years until maybe, possibly, they encounter another star system. Dr. Chandra Wickramasinghe, a long-time proponent of panspermia, released a statement calling 3 I/Atlas potentially the most significant event in astrobiology since the discovery of extremophiles. He might be overstating it. Chandra has a tendency toward enthusiasm, but he's not entirely wrong. If life or its precursors can travel between stars on objects like this, then the origin of life becomes a much more complicated, much more interesting question. Did life arise independently on Earth? Or did it start somewhere else and get delivered here on an ancient interstellar visitor we might never know. But 3i/Atlas proves the delivery mechanism is plausible. What we're doing about it. The astronomical community has taken 3i/Atlas as a wake-up call. We weren't ready for this. We got lucky that Atlas spotted it early. Lucky that it had a long, slow approach that gave us time to study it. But what about the next one? What if it comes in faster, at a steeper angle, giving us only weeks or days of warning? The Vera Rubin Observatory in Chile is scheduled to begin operations in 2025. It's specifically designed for survey work, scanning the entire visible sky every few nights, looking for anything that moves or changes. Its detection rate for interstellar objects is estimated to be 10 to 100 times better than current systems. We might go from seeing one interstellar visitor every few years to seeing dozens per year. That's exciting and overwhelming in equal measure. More data, more opportunities to understand these objects, but also more mysteries, more anomalies, more events like 3i/Atlas that defy easy explanation. There's also a proposal still in early stages for a rapid response space mission. A spacecraft kept ready to launch on short notice, equipped with instruments to rendezvous with interstellar visitors and study them up close. Maybe even collect samples. The mission is being called Bridge because it would bridge the gap between star systems, studying the objects that travel between them. It's ambitious, it's expensive, it probably won't get funded for years, if ever, but the fact that people are seriously proposing it tells you how much 3i/Atlas has changed the conversation, the question you can't stop asking. Late at night, when the data analysis is done and you're just sitting there thinking, the same question keeps surfacing: are we alone? Not in the "is there life on other planets" sense. That's a question about biology and chemistry and whether conditions elsewhere can support organisms. That's important. But it's not what 3i/Atlas makes you wonder about. No, the question is, are we alone in noticing? Are we the only civilization in the galaxy that's watching the sky, tracking these interstellar visitors, trying to understand what they are and where they came from? Or are there others out there doing the same thing we're doing, watching their own version of 3i/Atlas pass through their star system and explode near their sun? And if there are others watching, did any of them figure it out? Did any of them look at their data and really know what they were looking at? Or are we all equally confused, all struggling with the same mysteries, all standing on our respective planets staring up at phenomena we can't quite explain? 3i/Atlas came from somewhere. It travelled for millions of years through the dark and the cold. It entered our solar system, looped around our sun, and destroyed itself in 3 precisely timed pulses. And now its fragments are heading back out into the galaxy, scattering across light years, carrying whatever secrets they hold to destinations we'll never know. Whether it was a comet or something more, whether its explosion was natural or designed, 3i/Atlas has taught us something profound. The universe is full of wonders we're only beginning to detect. Objects are travelling between stars, materials are mixing, and we, standing here on our small blue planet, have finally developed the technology to watch it happen. So keep looking up, keep watching, because somewhere out there, right now, another visitor is on its way. Another mystery is falling toward our sun. And when it arrives, we'll be ready to ask the questions, even if we're not ready for the answers.